Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about Lewis structures with the specific focus on the elements that love to break the rules. So there's going to be three common types of ways we tend to break the octet rule. And in almost all of these cases, we're going to be doing this to help stabilize formal charges. Because again, it's worth noting atoms don't like to have an excess of positive or negative charge. And so if that means that occasionally they don't always have 8 electrons around them, sometimes that's good enough. So one of the first major groups that tend to break the octet rule is heavy elements, specifically elements of the third period or lower. So think aluminum, silicon, sulfur, chlorine. Most of your halogens, except for fluorine, most of these elements are fairly big, and as such, they can actually accommodate a fair number of additional electrons. So let's go ahead and look at our good old friend perchlorate. So perchlorate is a chlorine atom surrounded by 4 oxygen atoms, with the chlorine making 7 bonds. Woo, 7 bonds, that's a lot. This means that it has 14 electrons coordinating to the adjoining atoms. So that's a little bit more than 8. But let's take a look at the formal charge. The formal charge, it has 7 bonds. It should have 7 valence electrons. And hey, they're the same. Chlorine here has a formal charge of 0. Not to mention, chlorine is fairly big, so it can bend the rules a little bit. And this isn't the only time where chlorine tends to exceed the octet rule. We also have chlorate, where chlorine has 5 bonds and 1 lone pair, giving us 12 total electrons, still more than the octet rule. But if you double check, this still gives a formal charge for chlorine of 0. And the same thing with chlorite. Again, 3 bonds, 4 lone pair electrons. That's still 10 electrons, still more than the octet rule, but formal charge still is 0. So despite the fact that that we may have exceeded the octet rule, the formal charges still look good. And this means that chlorine's going to be relatively happy. Now, the question is, why do the rules not apply for these heavier elements? And one good way to look at it is that these heavier elements have empty d orbitals. So chlorine specifically has a set of 3 d orbitals with no electrons in it. So if it lets the electrons from oxygen occasionally hang out in its d orbitals for a little bit of time, just to make sure its formal charge is okay, I mean, why not? It'd much rather do that than have to deal with it, either a positive or negative charge around itself. So it works out fairly well. However, chlorine isn't the only element that can pull this off. We also have things like sulfur, which can bond to 6 fluorines to make sulfur hexafluoride, or bond to a whole bunch of oxygens to make sulfuric acid. This is the quintessential oxy acid. Or phosphorus, which can do the similar thing by bonding to 4 oxygens as well to make phosphoric acid, which actually coincidentally is what makes Coca-Cola taste so sour and tangy. And these compounds are actually fairly common. Now, it is worth noting that one of the things that does make this octet rule exception a little easier is that when we're dealing with these heavy elements, they're typically going to break the octet rule when they need to coordinate to multiple highly electronegative elements. And a good way to think about it is if I'm dealing with, say, sulfur bound to fluorine or oxygen, then what ends up happening is that oxygen is going to want those electrons a fair bit of the time. So even in this case, if we count around sulfur, it's got 6 bonds, which should be 12 electrons. But those electrons aren't going to be spending most of their time around sulfur. They're going to spend a fair bit of that time around oxygen, making it a little bit easier for sulfur to violate the octet rule. In addition, sulfur and phosphorus still have those empty d orbitals to give them a more wiggle room. And so while smaller elements like nitrogen, oxygen, or carbon can't pull this off. When you go to the heavier elements, the rules relax a little. However, only expect the octet rule to be violated for these heavy elements in cases of high when coordinated to highly electronegative elements, and make sure that it has a formal charge of 0. If all of those conditions are satisfied, yeah, we can have these excess number of electrons. However, just like elements can have an excess number of electrons, sometimes you can have fewer than 8 electrons. And one of the classic violations of the octet rule is if I've got elements that tend to have less than 4 valence electrons. And one of the reasons why is in order to form a bond, most elements have to put in an electron to get an electron back to form the bond. So if I only have 3 valence electrons, like most of our group 3 elements, well, then I can only form 3 bonds. So looking at, say, aluminum chloride. Aluminum only has 3 electrons, so it can only recruit 3 chlorines to hang out with them. It isn't popular enough to get a 4th chlorine. And we see a very similar thing with boron. And the only time we tend to see these elements be able to achieve a 4th bond is if they coordinate with another species that has those extra electrons. So for example, occasionally you may see something like borohydride, where we have boron coordinated to 4 hydrogen atoms. But really what ended up happening is I had a negatively charged hydrogen called a hydride, which came in with its negative charge and say, hey, boron, I've got the electrons if you can put up a place to stay. And boron, with its with its not satisfying the octet rule, can let other species come in. But it is worth noting that borohydride is considered fairly reactive because the hydrogen isn't going to stay there for that long before it finds a better place to stay. And one of the reasons why they tend to be fairly popular in chemical syntheses, because it does tend to fall apart. Because in general, group 3 elements like having 3 bonds. It's just the way that's going to make sure they have a formal charge of 0. Anything else, and like borohydride, you get a negative formal, you have a negative formal charge on a very electropositive element, and that's just not favorable. Then we have our last exception to the octet rule, and this is simply the case where if I have an odd number of electrons on my molecule, I can't make it so that every atom has an even number of electrons. It becomes a game of musical chairs. If you don't have enough chairs, somebody's going to lose out. And these tend to almost always form very highly reactive species that we call radicals. So a radical is a way to talk about a chemical species that has a lone unpaired electron. So let's take a look at nitric oxide, where we have a total of 11 electrons around nitrogen and oxygen. And since oxygen is more electronegative, it essentially says, nitrogen, you don't get as many electrons as you want, so haha on you. That said, it is worth noting in this case, both species do have a formal charge of 0, so they are fairly happy. However, that said, nitric oxide is known for being fairly reactive, as well as other species like the hydroxy radical, where we have oxygen and hydrogen have 7 electrons, and hydrogen needs to have at least 1 electron to make a bond, so oxygen loses out. And nitrogen dioxide, which has 17 electrons, where again, nitrogen loses out to maintain its neutral formal charge as neutral formal charge, as well as the fact is it simply isn't as electronegative as its 2 adjoining oxygen atoms. And again, in these cases, we tend to form very unstable molecules that are going to want to go out, complete their octet rule, but last long enough that we can see them. And in general, the formation of these radical species is going to happen most commonly when we have an odd number of atoms with an odd number of electrons. So if you ever see an odd number of nitrogens with an even number of hydrogens, watch out. Or an even number of nitrogens with an odd number of hydrogens. This means that when I count up my total number of electrons, we may have an odd number, so somebody's always going to be unhappy. So if you're not able to build a good Lewis structure, one of the things you should make sure you're looking out for is, do I have a heavy element with a lot of other electronegative atoms like oxygen? Do I have a group 3 element which simply isn't going to be able to bond to enough other things? Or do I have an odd number of electrons? If those are the case, you may have to break the octet rule to make a good structure. However, so far, all of our structures have been two-dimensional. Turns out we don't live in a two-dimensional world. So next time, we're going to bring in a third dimension and see what molecules might look like in real space. Until then, take care.